Hello everyone and welcome back to today's lecture on energy efficient buildings. My name is Mohammad Ehtisham and our focus today will be on lecture 34, our new module 11, Building Codes and Standards. Building energy codes play a vital role in promoting energy efficiency and sustainability in the built environment. As minimum energy performance standards for the design and construction of new buildings and renovations, these codes directly address the significant energy consumption and environmental impact associated with the building and infrastructure sector. Previously, we have already discussed energy auditing and performance management in context with smart building technologies and explored the possibilities for energy efficient in buildings and sustainability. The overview of building energy codes provide a comprehensive introduction to the importance, development, adoption, compliance and enforcement of these codes, highlighting their crucial role in helping us tackle our energy, economic and environmental challenges. The outline of this lecture will be starting with building energy codes, its importance and its purpose, international, national and local energy codes, compliance pathways and requirements, future directions in building energy code implementation. To start with, let's discuss with the impact assessment. The comprehensive study of impact assessment of energy efficiency measures in India for fiscal year 22-23, commissioned by Bureau of Energy Efficiency (BEE), evaluates the impact of energy efficiency measures implemented in India. The assessment reveals noteworthy progress in sustainable energy consumption and environmental preservation, demonstrating the effectiveness of national policies and initiatives across multiple sectors. Key findings include substantial energy savings, monetary benefits, and reduced CO2 emissions, highlighting India's commitment to energy conservation and climate change mitigation. The assessment of India's energy efficiency initiatives for the year 22-23 reveals significant achievements in energy savings and environmental impact. The total energy savings amounted to 50.81 million tons of oil equivalent, underscoring the country's progress in energy efficiency. This includes thermal energy savings of 25 million, which have contributed to reduced fossil fuel consumption, enhanced industry efficiency. Additionally, a substantial 307 billion units of electricity was saved, reflecting the widespread adoption of energy efficient practices and technologies across various sectors. These achievements highlight the effectiveness of India's energy efficiency measures, which have also resulted in considerable monetary savings of 188,312 crores. This financial benefit illustrates the economic viability of substantial and sustainable practices and energy conservation efforts, befitting consumers and businesses while contributing to the country's overall economic growth. The reduction in energy cost allows businesses to allocate resources to other development areas, potentially increasing productivity and competitiveness in the global market. Moreover, one of the most significant outcomes of these measures is a substantial reduction in CO2 emissions, with an annual decrease of 306 million tons in the financial year 22-23. This achievement is crucial for India's climate change mitigation efforts and contributes to global environmental preservation. The reduction in emissions is attributed to the adoption of cleaner energy sources, improved industrial processes, and implementation of energy efficient technologies across different sectors. This accomplishment aligns with India's commitment under international climate agreements and showcases the country's proactive approach to addressing the global environmental challenges. Sectoral contributions to energy efficiency. Let's start with industry. The Perform, Achieve and Trade PAT scheme has been instrumental in driving energy efficiency in the industrial sector. Multiple cycles of PAT have been implemented, targeting energy-intensive industries and contributing significantly to the overall energy savings. The PAT scheme has successfully encouraged industries to adopt best practices and invest in energy-saving technologies, resulting in measurable reductions in energy consumption. This scheme has proven effective in fostering a culture of energy efficiency among industrial players and contributing to India's broader energy conservation goals. Buildings. In the residential and commercial building sector, the Energy Conservation Building Code or ECBC and Eco Niwas Samhita ENS programs have been pivotal in achieving substantial energy savings and emissions reductions through improved building design and operations. ECBC and ENS have promoted the use of energy efficient materials, technologies, and building practices, leading to significant reductions in energy consumption and greenhouse gas emissions. These codes have played a crucial role in shaping the construction industry towards sustainable and environmentally responsible practices. Transport and municipal. The transport sector has benefited from the initiatives like corporate average fuel economy or CAFE norms and the faster adoption and manufacturing of hybrid and electrical vehicles FAME scheme. Municipal and agricultural sectors have seen improvements through municipal demand side management and agriculture demand side management programs. These programs have contributed to a shift towards cleaner and more efficient transportation options, promoting the adoption of electric vehicles and reducing fuel consumption. In the municipal and agricultural sectors, MUDSM and AGDSM have encouraged energy conservation practices and improved energy efficiency in various activities, leading to sustainable resource management. Why building energy codes are important? Let's discuss. Building energy codes play a crucial role in shaping the future of sustainable construction, promoting energy efficiency, and fostering a more environmentally conscious building sector. These codes establish minimum energy performance standards, effectively reducing energy consumption in buildings. By setting a baseline for energy efficient design and construction practices, building energy codes drive the adoption of innovative technologies and sustainable building materials, ultimately contributing to a more energy efficient built environment. The environmental impact of building energy codes extend beyond energy savings, contributing to significant reductions in greenhouse gas emissions. By minimizing the environmental footprint of the building sector, these codes align with global efforts to combat climate change and promote a greener future. The widespread adoption of building energy codes fosters a collective commitment to sustainability, ensuring that the built environment becomes a driving force in achieving environmental goals. Beyond environmental benefits, building energy codes offer tangible economic advantages. Energy efficient buildings result in lower utility bills for owners and occupants, generating long-term monetary savings and improving the economic viability of sustainable construction. This cost effectiveness not only incentivizes developers to embrace sustainable practices but also makes energy efficient buildings more attractive to investors and tenants, contributing to the overall financial sustainability of the building sector. Building energy codes serve as a powerful regulatory instrument for governments to mandate energy and efficiency in the building sector. They act as a vital policy tool to achieve national emission reduction targets and sustainability goals, ensuring that the building sectors play a key role in the transition towards a more sustainable future. By providing a cleaner framework for energy efficiency, building energy codes create a level playing field for all the stakeholders, encouraging innovation and driving the industry towards a more sustainable path. International energy codes. The International Energy Conservation Code IECC and ASHRAE Standard 90.1 are two prominent international energy codes that provide minimum energy efficiency requirements for the buildings. The IECC, developed by the International Code Council, covers both residential and commercial buildings, while ASHRAE 90.1, created by the American Society of Heating, Refrigerating and Air Conditioning Engineers, focuses on commercial buildings. Both codes are updated on a regular basis, typically every 3 years, to incorporate new technologies and practices that enhance energy efficiency. They serve as model codes for many countries and local jurisdictions worldwide, which often adopt them to suit their specific climatic conditions, construction practices, and energy efficiency goals. The IECC and ASHRAE covers various aspects of building design and construction, including the building envelope, HVAC systems, lighting, and other energy consuming systems. The widespread adoption of these codes have facilitated knowledge sharing and standardization of energy efficient building practices across the borders, contributing to the global effort to reduce energy consumption and greenhouse gas emissions in the built environment. National Energy Codes, Energy Conservation Building Code ECBC. The Energy Conservation Building Code (ECBC) is India's national standard for energy efficient building design and construction. Developed by the Bureau of Energy Efficiency (BEE), the ECBC establishes minimum energy performance standards for the commercial buildings in India. The code covers various aspects of building design, including the building envelope, HVAC systems, lighting, electrical systems, and renewable energy integration. It aims to reduce energy consumption in buildings, promote sustainable building practices, ultimately contributing to India's broader energy efficiency and climate change mitigation goals. The ECBC impact extends beyond the technical requirements it sets. It serves as a catalyst for innovation in the building industry, encouraging the development and adoption of new energy efficient technologies and materials. The code implementation has fostered a culture of sustainability in the Indian construction sector, leading to a shift towards more responsible building practices and a greater awareness of energy efficiency. While the ECBC is developed at a national level, its implementation is the responsibility of state and local governments. This approach allows for adoption of regional climatic condition and building practices, ensuring that the code is both effective and feasible across India's diverse geographic and climatic zones. The code undergoes regular updates to incorporate technological advancements and aligns with India's evolving energy efficiency goals, making it a dynamic tool in the country's efforts to promote sustainable building practices. The ECBC is a comprehensive set of guidelines that addresses key elements of building design, construction, and operation to reduce energy consumption. These elements include: number 1, building envelope. The ECBC specifies requirements for wall, roof, and fenestration assemblies to minimize heat gain and heat loss, improving overall building energy efficiency. These requirements can include insulation levels, window glazing specification, and shading strategies. For instance, the code may stipulate the use of high performance glazing that reduces solar heat gain while maintaining natural light levels. The code's provision for the building envelope are designed to optimize thermal performance, minimizing energy demand for heating and cooling while maintaining comfortable indoor conditions. Next, HVAC systems. The code sets standards for heating, ventilation, and air conditioning systems, promoting the use of energy efficient equipment and control strategies. The ECBC encourages the use of high efficiency HVAC systems such as variable speed drives and smart control system, which can optimize energy consumption based on occupancy level and weather conditions. Additionally, the code may mandate the implementation of heat recovery systems to reclaim wasted heat energy. The ECBC's provision for HVAC systems aims to minimize energy consumption through efficient system design and operation, promoting technologies that reduce reliance on fossil fuels and enhance indoor air quality. Next one is lighting. ECBC mandates the use of energy efficient lighting system and controls, including requirements for daylighting in applicable spaces. These include specifying minimum requirements for energy efficiency in lighting fixtures and promoting the use of daylight strategies, such as designing buildings with large windows and skylights to maximize natural light penetration. The code also encourages the use of occupancy sensors to automatically adjust lighting levels based on the room occupancy, further reducing energy waste. The ECBC's focus on lighting promotes the use of energy efficient technologies and design principles that maximize natural light and reduce reliance on artificial lighting. Next is renewable energy. The code encourages the use and integration of renewable energy systems such as solar photovoltaics to offset building energy consumption. The ECBC provides incentives for incorporating renewable energy sources into the building design, such as offering tax credits or rebates for solar panel installations. It also includes guidelines for the integration of solar thermal systems for water heating and other applications. The ECBC's provision for renewable energy encourages the adoption of sustainable energy sources, reducing reliance on conventional energy sources and promoting a transition to a cleaner and energy future. Next is electrical systems. The ECBC promotes the use of energy efficient electrical equipment and appliances, including energy saving features in lighting and HVAC system. This includes encouraging the use of energy efficient motors, transformers, and other electrical equipment. The code also emphasizes the importance of energy management systems that can optimize energy consumption within the building. The ECBC's provision for electrical system focuses on reducing energy consumption with efficient equipment and technologies, enhancing energy management practices within the buildings. Local energy codes in India, state-wise implementation. The implementation of ECBC in India varies across states, reflecting the diverse challenges and priorities in different regions. As of March 2023, 22 states and 2 union territories have notified ECBC, demonstrating significant progress in the nationwide adoption of energy efficient building practices. However, the level of implementation and enforcement differs among these states. Andhra Pradesh leads in ECBC implementation with 352 compliant buildings, followed by Punjab with 133. Other states like Telangana, Haryana, and Kerala has also made notable progress. The varying levels of implementation can be attributed to factors such as local government capacity, availability of technical expertise, and the prioritization of energy efficiency in state level policies. Efforts are ongoing to increase ECBC adoption and compliance across all these states, aiming for comprehensive nationwide implementation of energy efficient building practices. States leading in implementation are Andhra Pradesh, Punjab, Telangana, Haryana, and Kerala have all shown significant commitment to ECBC implementation with varying numbers of compliant buildings. Challenges and opportunities. The implementation of ECBC faces challenges including limited awareness among stakeholders, lack of financial incentives, and the need for robust enforcement mechanisms. Policy initiatives. Various state level policies and programs aim to promote ECBC adoption, including providing financial support, technical assistance, and capacity building initiatives. Continued efforts are needed to enhance awareness, capacity building, and enforcement, ensuring the effective implementation of ECBC across all these states. Moving ahead, Chhattisgarh State Supply Electricity Code. The Chhattisgarh State Electricity Regulatory Commission has notified the State Electricity Supply Code to govern electricity distribution and supply in the state. This code serves as a vital regulatory framework outlining the practices for distribution licenses to provide efficient, cost-effective, and customer-centric services within the electricity sector. The supply code encompasses various aspects of electricity distribution, including metering, billing, and consumer rights. The Chhattisgarh State Electricity Supply Code has undergone several revisions to address the evolving needs and challenges within the power sector, with the latest revision being the 4th Amendment in 2024. This amendment highlights the dynamic nature of the energy sector and the necessity for continuous adaptation of the regulatory frameworks. The implementation of the supply code has resulted in improved electricity distribution practices and enhanced consumer services in Chhattisgarh, contributing to the overall efficiency and reliability of the state's power sector. The supply code aims to achieve several key objectives, including promoting competition within the electricity sector, ensuring transparency and accountability in distribution operations, and safeguarding the interest of consumers. The code establishes standards for metering, billing, and dispute resolution, while also defining consumer rights and obligations. By establishing a clear framework for electricity distribution, the supply code aims to cultivate a more efficient and reliable power sector in Chhattisgarh. This fosters the state's ability to meet its growing energy demands and contribute to sustainable development goals. The Chhattisgarh State Electricity Supply Code has played a significant role in promoting energy efficiency in the state. It encourages the adoption of energy-saving technologies and practices, contributing to the overall reduction of carbon emission. The code aligns with the state commitment to sustainable development and its efforts to address the climate change. This approach strengthens the state's position in a global movement towards a more sustainable energy future. Energy Conservation Building Code ECBC 2017 update. The 2017 update of the Energy Conservation Building Code ECBC represented a significant step forward in India's commitment to building energy efficiency standards. This revision, incorporating cutting-edge technologies, introduced a tiered approach to energy efficiency as ECBC, ECBC Plus, and Super ECBC. This tiered frameworks allows for a gradual progression in building energy performance, providing a pathway for buildings to achieve higher levels of energy efficiency over time. This strategic approach not only promotes sustainable development but also fosters a more sufficient and reliable power sector. The ECBC update included notable changes in compliance methods. It allowed for a choice between a prescriptive approach, which outlines specific requirements for building components, and a simulated baseline building calculation, which utilizes energy simulation software for evaluating energy performance. This flexibility empowers designers to design the most suitable method based on their project's unique requirements while adhering to energy efficiency targets. The scope of the code extends to various aspects of building design, including the envelope, lighting design, HVAC, electrical system, and renewable energy integration. This comprehensive approach has significantly impacted building design and construction practices across India, ushering in a new era of energy efficient building design and construction. The importance of building energy codes. The ECBC update serves as a critical component of India's overall energy efficiency strategy, aligning with the nation's commitment to sustainable development and its effort to combat climate change. It encourages the adoption of energy saving technologies and practices, playing a crucial role in reducing carbon emission. By setting clear standards for building energy performances, the ECBC promotes the use of sustainable materials, efficient building systems, and renewable energy sources. The implementation of these codes create a more sustainable building sector, contributing to a greener and more energy efficient India. This is the basic compliance level, setting minimum energy standards for the buildings, followed by ECBC plus level. This is the intermediate level, requiring higher energy efficiency performance than the basic ECBC level. Last one is super ECBC level, highest level of energy efficiency, representing best-in-class building performance standards. Let's move ahead with compliance pathways for building energy codes. Building energy codes typically offer multiple compliance pathways to accommodate diverse building design and construction approaches. The four main compliance pathways are prescriptive, simple trade-off, performance-based, and outcome-based. Each pathway has its own advantages and is suitable for different types of projects and design teams. The prescriptive approach specifies minimum or maximum values for discrete building components, making it straightforward to implement but less flexible. It sets clear rules for specific elements like insulation thickness, window glazing, and lighting efficiency. While this approach simplifies compliance, it may limit the architect's creative freedom and could result in overly prescriptive designs that are not optimized for specific building types or climates. The simple trade-off method allows for some design flexibility by permitting trade-off between similar building components. For example, allowing a larger window area if a highly efficient glazing system is used. This approach offers a balance between prescriptive rules and design freedom, enabling architects or designers to make design choices based on cost-effective energy-saving solution. Performance-based compliance. Performance-based compliance requires energy modeling to demonstrate that the proposed design meets or exceeds the energy performance of a reference baseline building. Architects and engineers use sophisticated software to simulate the building energy use, taking into account factors like climate, building materials, and system efficiency. This approach promotes innovative design and encourages the use of advanced energy-saving technologies. However, it requires significant expertise in energy modeling, which can be costly and time-consuming. Lastly, the outcome-based approach focuses on actual building performance post-construction, typically through energy performance certificates or disclosure of consumption data. This pathway incentivizes continuous improvements and energy management by holding building owners accountable for their energy usage. It can also encourage the use of smart building technologies that optimize energy use based on real-time performance data. This approach often requires ongoing monitoring and verification of energy performance, which can be challenging to implement and maintain. Type of building energy codes and standards. Building energy codes and standards can be categorized into three main types: mandatory codes, voluntary codes, and stretch codes. Each type serves a specific purpose in broader landscape of building energy efficiency, regulation, and promotion. Mandatory codes are legally required energy efficiency standard that must be met by all new construction and major renovation within a jurisdiction. These codes establish the minimum acceptable level of energy performance for buildings. Mandatory codes are legally required energy standards that this codes establish the minimum acceptable level of energy performance for building. Its example include the Energy Conservation Building Code ECBC in India, which sets minimum energy standards for building. This code is legally required for all new construction and major renovation. Another example is the International Energy Conservation Code IECC in the US, which has been adopted by many states and local jurisdictions. Voluntary codes, on the other hand, are optional guidelines that encourage high level of energy efficiency beyond the mandatory requirement. These codes often serve as a precursor to future mandatory standards and allow for market adaptation to more stringent energy efficiency practices. Stretch codes represent advanced energy efficiency standards that reach beyond minimum standards to achieve higher energy savings. These codes are often adopted by progressive jurisdictions aiming to lead in sustainability efforts and can serve as a model for future updates to mandatory codes. A notable example is the statewide implementation of ECBC in India, which sets ambitious targets for energy saving. The codes are often adopted by jurisdictions committed to environmental sustainability and pushing for higher levels of energy efficiency in the built environment. Implementing building energy codes key factors. Building energy codes are crucial for sustainable development, reducing energy consumption in buildings. Effective implementation requires a multifaceted approach. The successful implementation of the codes depends on several key factors. Establishing robust institutional structure is crucial, involving governmental and regulatory frameworks to oversee code development, adoption, and enforcement. These structures ensure consistency and accountability in the application of energy codes across different jurisdictions and building types. For example, ECBC in India is overseen by BEE, which ensures compliance through a system of inspection, certifications, and penalties. Developing comprehensive building energy code necessitates collaboration among experts, stakeholders, and industry professionals. These ensure codes are practical and adaptable to diverse building types and regions. Adopting building energy codes into local regulation and policies is essential for widespread implementation. This involves incorporating codes into building permits, zoning ordinances, and legal frameworks. Government play a crucial role by providing incentive, support, and education. Implementing these codes involves practical application in design, construction, and building operation. This includes utilizing energy efficient materials, technologies, and construction techniques. Professionals need training to ensure projects meet these standards. Accessible resources such as software tools, simulations, and online database can facilitate implementation. Enforcing these codes is vital to guarantee their effectiveness and ensure building meets energy performance targets. This involves systematic verification of compliance through inspection, performance testing, and certification programs. Building codes play a crucial role in enforcing codes and ensuring adherence to standards. Continuously evaluating the effectiveness of these codes is essential to ensuring relevance and adaptation to the evolving technologies and practices. This involves assessing the impact on energy consumption, reviewing technological advancement in energy efficiency, and incorporating new data in the code updates. The future of building energy code implementation is likely to see significant advancement in several key areas. Enhanced compliance systems are being developed, incorporating more sophisticated methods for tracking and verifying code compliance. These systems may include digital platforms and automated assessment tools that streamline the compliance process and improve accuracy. The integration of smart technologies and IoT devices is expected to play a crucial role in optimizing the performance and facilitating real-time monitoring and adjustment of building systems. Adaptation to climate change is becoming an increasingly important consideration in building energy codes. Future codes are likely to incorporate resilience measures and adaptive strategies to address varying environmental conditions and extreme weather events. There is also a growing trend towards the harmonization of standards across different jurisdictions, aiming to streamline implementation and foster knowledge sharing on a global scale. This harmonization could lead to more energy efficiency practices and consistent being towards region and countries. Despite the clear benefits of building energy codes, their implementation faces several challenges. One significant obstacle is the lack of awareness and understanding among stakeholders, including builders, architects, and local authorities. This knowledge gap can lead to resistance to adoption and incorrect application of code requirements. Additionally, the initial costs associated with implementing energy efficient measures can be deterrent for some builders and developers, especially in markets where energy efficiency is not highly valued by consumers. In conclusion, the future of building energy code implementation is poised to significantly enhance energy efficiency and sustainability across the built environment. By developing enhanced compliance system, integrating smart technologies, adapting to climate change, harmonizing standards globally, we can ensure that building energy codes remain a vital tool in addressing our energy, economic, and environmental challenges. These advancements will not only streamline the implementation process but also foster innovation and resilience, ultimately contributing to a more sustainable future. As we move forward, it is crucial for stakeholders at all levels to collaborate and embrace these future decisions to maximize the benefits of building energy codes. In the upcoming lecture, we will explore the key requirements for achieving energy efficiency, strategies for complying with energy codes, and the role of energy modeling and simulation in the compliance process. This concludes our learning of building energy codes overview for energy efficient buildings. Thank you for your attention.